continue with what we were talking last time. We started with simulating a plate with a hole under tension. Okay, so we'll just take a look at how you can solve these types of problems in Abacus, and then we'll go over this term project that I've just handed out. All right, so let's see. So, all right, so last time I was telling you about most of these, uh, how you can access information about most of these capabilities of Abacus. And I told you that this is the manual that you first need to pay attention to, the Getting Started with Abacus Interactive Edition. So let's go there. And we talked about how is this Abacus routine structured. So essentially all finite element routines, all finite element packages, all they do is you need to generate some type of an input file. Okay, and that input file is going to go into all these analyses subroutines, and once you are done with your analysis, you have to do some visualization. So in the codes that we wrote, we just wrote one set of Fortran code that did all three of these things. Actually, modeling was not so much done in the code. I gave you the input file, you read the input file and analyzed it, and then plotted the results. Okay, so this is sort of the overall structure of any finite element program. And then we talked about how, let's see if we can, these Abacus basics. So this is the same type of routine. And what are the components of an Abacus model? So in Abacus, last time maybe I showed you this, that there is this on the left side window. We have this tab which denotes your model. This is the overall sort of conceptual model of the problem that you are trying to solve. So this model contains different parts. It can contain different materials, and I told you that the way to think about these sections is that you're assigning a particular material to a particular element. So that's the section type of thing. And then assembly is where you take all your parts in your model. So for example, if you have an automobile, you have different parts of your automobile, you put them together, that will make up your entire finite element model. So this is the assembly routine. In steps, what we do is we define the type of analysis that we are going to do. So we can say that if we have a beam, we are going to apply compression first. That's step one. Then we are going to apply shear. That's step two. So in every different step, you can organize your final analysis in different number of steps. Some steps could be just static. Some step could be dynamic. So maybe you could say that, well, I'll take my beam, I'll pull it down on one end, and then the next step, I'll just leave it. So that next step will become dynamic, and you'll see how you can do how you can mix and match these different types of analyses. So obviously, our code does not have all these capabilities, and but essentially, the underlying theory you should be familiar with now. All right, so going back to the manual, where is that? All right, so we have the discretized geometry, element section properties, loads, boundary conditions, analysis type, and output requests. So output request is nothing but just like in our code, we had that lm post subroutine where we were returning displacement, we were sending in displacements and returning the stresses at the nodes. So in general, a finite element program can create a huge amount of data. Every Gauss point, every node, you can get multiple different variables that you might be calculating. So you have to choose this output requests carefully so that the files, output files, don't just completely blow up in size. All right, so let's take a look at this. This 2.2 is the section that describes how Abacus sort of works. And I told you last time that there are all these different modules in Abacus, and we started to model this uh, geometry with all these modules. So maybe it's just better to quickly go over how to create the model again. So the first module is part, and this button creates a part. If I click this, three-dimensional, deformable, solid, and type extrusion. So I told you last time you can sketch out a two-dimensional part and extrude it in the third dimension to create a geometry. So, and the approximate size is 200. Again, the units are free, sort of. You have to choose your own units. Okay. All right. So let's say you can create this uh, domain or rectangular domain, and maybe we can create a hole inside this. So again, all these information, it gives you what to do. So pick the center, pick a radius. Let's say this is the radius, and then I'm going to say done. And now it's going to ask me for what is the depth you want to extrude it to. So let's say maybe 2. Um, and this is the plate that we had ended up with last time. Okay, and now we are going to create a material. So let's say the material type is steel. There are all these different materials that we talked about last time, but we'll stick with linear elastic material. It's isotropic. Um, so the the modulus that we'll use is 2,210 gigapascal for steel, and zero point 0.3 is the Poisson's ratio. So now we have one material, and going to the next drop down box in this, all that we have done till now is we have created the part and we have created one material. Now we are going to assign this material to this part, and to do that we need to create a section. So let's say steel section, solid, homogeneous, and this creates a steel section. So once we have created a steel section, we can assign it to a part. So all that we did till now is just went through these 3 buttons in a line. And as you keep on using Abacus, you'll get more and more familiar with what are all these different things. So as soon as I click this, it says select the regions to be assigned a section. So I place my mouse over this and select that whole domain, click done. And since there is only one steel section, we are saying that this entire model is made out of steel. So then now we have assigned the material property steel to this entire part. Okay, and so next thing, go to assembly, and we talked about how you can create an instance of a part. All that we have done till now is created a part. Now we are going to create multiple instances of these parts, uh, and we can keep this option dependent mesh on part, meaning whatever mesh we generate is going to be dependent on this. So okay, and since there is only one part in this problem, I don't have to do any assembly or anything. So in general, if you have multiple parts, there are multiple different ways of doing this assembly. You can take a look at the other buttons in here. So the next button down is step. And here is where we are defining boundary conditions and loads and what is the type of analysis that we are going to do. So this button says create step. By default, there is always one step that is already there. This is the initial step. So we'll create one more step, and let's say that we are going to apply a static load. So we'll say that this is a static general type of step. You can see all these other different types of steps that you have here, dynamic, heat transfer steps. The static RIX is for mainly for nonlinear problems, but let's say just static general. Um, and we'll name this step as load. So you can say that you can give some description of this step, and there are other different parameters that you actually don't have to mess with right now, but if you keep it as just the most basic analysis, it should run for this type of a simple problem. So another thing here is that there is this button called NL Geom. What this does is it activates the large deformation analyses. So this makes it non-linear. So in our case, we'll just keep it off. Okay. So now that we have created the two steps, all that we need to do now is define our boundary conditions and loads. So go to the next step. This is interaction. Interaction is usually needed. We need to define interaction when we have multiple different parts. If you have 2 or 3 different parts, they might be coming into contact. There might be friction between them. So those are the types of things that you might need to define in interaction. But in this case, again, there is just one part, so we don't need to define any interaction. We'll go to the next step, that is load. And now we define the boundary conditions. So creating a boundary condition, let's say left fixed, and it asks me in which step do you want to calculate, do you want to enforce this boundary condition. So I'll say initial, the boundary condition we usually create in the initial step, and category of this boundary condition is it's a mechanical boundary condition, and we are going to specify displacement and rotation to fix the boundary. So continuing like that. Now it asks me to select the regions for the boundary condition. So since I want to have my left end fixed, I'll go to this button, rotate my domain to face the left face, and then I'm going to unclick this, and let's say get rid of this, and then select the regions for the boundary condition. If I place my mouse over this face, it marks that, and now I can say done. So now it is going to ask me what are the boundary conditions that you want to enforce on this face. So I'm going to say that U1, U2, U3 displacements in all 3 directions at every point on this face should be 0. Okay, so all done, and that creates this boundary condition. So next step is to create the load. Click the load manager, create, and let's say right face load. And we will create this load in the load step. Okay, and this is a mechanical load, and it is of type, let's say, pressure. There are all these different types of loads that you could apply: concentrated force, moment, surface traction, body force, all these different types of things. So in our case, what we are trying to do is apply this type of a tension to this plate. And so we'll choose this pressure and continue. So now it asks me select the surfaces for the load that you want to apply. And again, we'll go to the opposite face. Select this surface and click done. And now it is asking me what is the load that you want to create. So let's say magnitude of this load, since it's a pressure, if I say a positive pressure, then it will be compressive. So what I'll do is choose a negative 10 to the power 6, let's say. So this is the magnitude of the pressure, and I'm applying a negative pressure, meaning I'm applying a tension to this face of this plate. Do you have a question?
What's the difference in like pressure and like surface traction?
Pressure and surface traction. So okay, so pressure is always going to be normal to the surface. Traction, if you have the surface, in general, when you say sigma applied on n, sigma n is traction, and that can be pointing in any direction. So if you're shearing it off and applying a normal force, it could point in a general direction. So this is the tension pressure, quote unquote, that we have applied to this bar, to this plate now. And to uh, basically now we are done with this step. There is a field output request, which is, let's see, in job, I think. Um, all right, so basically now that we've defined our mesh and boundary conditions, we need to mesh it, so load and boundary conditions, we need to generate a mesh on this domain. So a couple of ways that Abacus uses to generate the mesh is to first create a seed. So what you're going to do is you're going to create a bunch of points all along the domain that Abacus is then going to use as a mesh seed. So you're going to seed your domain first. Um, okay, so let's say we, it says we need to make the mesh independent of that. So in assembly, I think, let's see, where is that? Um, right, yeah, right. Okay. Um, create options. So where do you do the make the mesh independent? Okay. Um, mesh tools, try operation, make independent from instance in the model tree. So this is the instance. Basically, we should have chosen make independent from the part. Um, uh-huh. Here. Okay. Um, so basically, let me actually try to delete this instance and recreate, regenerate. Okay. Delete. Let's delete. Okay. So let me just create a new instance now. Um, and now I can choose independent mesh on instance. All right. And hopefully the load and the boundary conditions should be the same. Right, load created. Okay. Um, and then we go to mesh. And so here it is asking you for, I'm just going to create a couple of seed points for the mesh. So it's approximate size of the mesh. In this case, you have to specify. So let's keep it at 3.8, which would be a very small element size. So you can see that these are all the different different points that Abacus created all along the domain. And another thing to note here is that on some of these buttons, there is a little this black triangle that you might see in the on some of these buttons. So if you click on this, click and hold this button, you will see that you can expand all these different things. So now I'm going to try to mesh this part instance. So Abacus asks me, is it okay to mesh this part? Say yes, and here we have a mesh. So automatically, basically, Abacus has generated this mesh for us. So the next step is job. Basically, all that we've done till now is pretty much created a model or that will write an input file just like the input file that we were using in our homeworks. So now we are going to submit that input file to uh, to Abacus. So let's create and we do that by submitting a job. So let's say plate with hole. Source is model. Full analysis. We want to run it in the background mode and submit time immediately. So you can change some of these parameters, but if you're doing a small problem, it shouldn't matter. So, okay, and now this is the window which allows you to submit the job. So we have just created a job, and now we are going to say submit. It's suppressed or deleted. Okay, so when I deleted the mesh, that got deleted. Nope. Um, Going back to the load module, here we need to make sure our boundary conditions and um, so right load is there, but boundary condition was not there. So we need to create a step, initial boundary condition, not sure what's, um, I did create a new load, right? Say that again? Okay, yeah, left fixed, propagated. We have to choose the surface again. Oh, yes. Okay, edit region. It does say that I've picked the region already. Okay, select the regions for the boundary condition. Okay, so it is suppressed. I think there is some trouble because of deleting the instance. Yeah, I mean,
It should be dependent instance, and you should then define the mesh control, and then see. Because I think we need now, because it's very simple, there is no independent instance, right? It should be dependent.
no, actually, both ways work. I tried this before some time, but I can't seem to remember what I did then. Um, so let me just quickly check if this works, and then we'll move on. Uh, Basically, what I'm describing to you here is a process that is already given in this example. 2 point, let's see. All right, so this is the example that you can follow, 4.3, and if you can just make a note of this example. Um, this pretty much leads you through the process of how to generate the geometry and the boundary conditions and all these different parts. But let's and finally, okay, edit. Yes. Region. Done. Okay. Dismiss. And finally, if I go to mesh, it's already there. Job is there. And if I say submit, okay. So now it says that the job has been submitted for analysis. And you can click on this monitor to uh, to see what are the updates. So the job has been started and it is already completed. Um, so now, since the job has completed, we can go back and take a look at the results from this uh, from this uh, button. And this results is also the same. The next module of all this drop down. It's visualization. So once you go to visualization, there are all these different types of things that you can visualize. So one way to see the deflected shape is this button, plot deflected shape, and you can see that it pretty much expands the mesh. And so this is the deflected shape. But just to get the similar type of plot that we were doing in the homework, we also plot the stresses on our deflected shape. So if you take a look at this thing in flat face front, so if you do that, you can see that you get some very coarse results from this example. Um, you have also a lot of different options in this. So there is this button called common options, and here it also shows you what is the deformation scale factor that it is using. In our analysis, if you remember, we were using deformation scale analysis, a magnification factor. Was it 20 or was it something else? Um, I think for the beam problem, we had chosen the magnification factor just to be 1. For the truss problem, that was somewhere like 20. So we can change this deformation factor, make it uniform, and instead of this 20,000, if we say 1, then you might not even be able to see the deformation. If I click OK, we see that the deformation and the undeformed shape and the deformed shape, there's not much difference in this. So the real deformation is very small. You can plot those magnification factors also. All right, so one thing that you can choose to do now is to plot different types of stresses. So here on the top menu, you have all these different quantities that of interest that you could probably plot. So let's keep it at S stress, and there are these different types of stresses that you could plot. Now these are the familiar stress components that we have from the Voigt notation, S, X, X, Y, Y, and so on. This Mises stress, how many of you have heard of von Mises stress? Okay, couple of you. So the von Mises stress is used for plasticity problems. Okay, um, this is a stress that when you reach this von Mises stress, your material at that point might start to yield. So in this case, if what this is plotting here is von Mises stresses, and you can see that this red region that is at the top of this curve that has the highest stress, positive stress, that is tensile. And the blue region, can't tell whether this is positive or negative. It looks like it's very small positive or negative number, so it's close to 0. And as it should be, what we are doing is we are holding this left end fixed, and we are applying a tension on this right edge. So on this circle, what happens is there is a stress concentration above and below this this hole. Essentially, the load is going to come like this and flow around the hole that causes this stress concentration. So you can actually theoretically show that for this problem, a plate with a hole under tension, um, this stress concentration here is 3 times the far field traction. So what we applied here was 10 to the power 6, which means that the magnitude of this red uh, should be equal to 3 times this far field applied load. And one way to check what is the value of all these things, you can go to tools, or you can go to tools and query, and you can probe for values at all these different points. So if I say probe for values and I want stress, then as soon as I go here, it is telling me what is the stress in this element. Um, you can take a look at the value of this Mrs. stress. This is for the element. So this element has 1.5, this has 1.5 again, and 1.67. If I change this to nodes, then it is an average value at the nodes. And if I go to this point, again, Mrs. stress, it is 1.569. And ideally it should be 3, but since this is a very coarse mesh, that's why we are not getting the 3 type of factor that we normally get for this type of problem. But if you refine the mesh, it becomes a very, let me see if I have that. So if you refine the mesh, you get a much better solution. So this is a highly refined mesh with different types of very much smaller elements and even quadratic elements. And this is a very regular circular hole where if you look at these values, these red, they are in the range of 3.39. So as you refine the mesh, your stress concentration around the hole gets better and better. So anyway, you can try this thing, and actually for this mesh you will not be able to use the uh, students version again. So you have to try to get access to ECN lab or that computational server interstate at interstate.ecn.purdue.edu. All right. So this is basically sort of how you would do a basic finite element analysis. And there are some other capabilities also in this. You can create a cut. So for example, if you click on this, it cuts part of your mesh, and it allows you to go in and take a look at particular values where you might be interested in. Okay. Um, so there are all these different types of post-processing techniques. You can explore that from this section that I just told you, section 4.3 in this Abacus Getting Started manual. I think a couple of other points that I wanted to mention here was just take a look at this section 3 also. Here, this section 3 defines uh, how Abacus can handle some finite elements and couple it with rigid bodies. So the way Abacus defines its finite elements is by defining all these 4 parameters. So first parameter is of a finite element is called its family. So these are these different families of finite elements that Abacus has. What we have been dealing till now is continuum finite elements, 2-dimensional, 3-dimensional continuum finite elements. In general, you can have plates and shells, you can have beam finite elements, you can have rigid elements, and all these different membrane, infinite, springs, and truss elements. So um, the way Abacus denotes all these different finite elements is also sort of described here. So for example, in 3 dimension, this is the most basic analog of what we had Q4, right? In 3 dimension, this would be Q8. Um, the way Abacus calls this element is C3D8. What that stands for is continuum finite element, 3-dimensional with 8 nodes. So that's how Abacus denotes all these elements. Similarly, this is C, continuum, 3-dimensional, 20 nodes. This is continuum, 3-dimensional, 10 nodes. and M stands for a modified formulation. There are so here is what the formulation that it describes, and different types of integration, whether it's full integration or reduced integration. Um, so you can take a look at these things and go through the example and try to build up a small example of follow this example and try to build up one of the examples that I've assigned for the term project. So maybe in the little bit of time that I have for discussing this, let's just briefly go over this. Um, so in this term project, basically what I'm asking you to do is use Abacus or any other program if you're familiar with that to solve a simple but practical uh, problem, which whatever you're interested in. So a couple of examples that I've given on the next page is a bolted riveted connection, or you can try to simulate a simply supported reinforced concrete beam. And then here on out, it starts to get a little more complicated. If you're going to do a beam column connection or a defective corbel. So those of you, how many of you attended the seminar yesterday? Okay, so that problem is right here. You can try to simulate, just model this thing, try to simulate what would be the forces in the anchors for the corbel. But so uh, this is a problem of a bolted riveted connection, bolted or riveted connection. You have two plates. You could have three, where you could have another plate on top here. They are all connected with n number of bolts. So the idea here is in this project that you're not just going to create one model, run it, get the analysis, and here's the result. That is not a valid or enough project. What you need to do is to study a certain aspect of a problem. What is the effect of some parameter on something that you are studying? So for example, in this case, if I'm applying this tension, pulling it apart, what is the effect of number of holes? What is the effect of how close I put the holes together? And how do I study that? So how do we even model this problem? What we have talked about in this course is a very simple single mesh and all these linear elastic models, small strain geometry and all that. How do we model this problem with, with the information that we have till now? So you would have to think about that a little bit. Maybe a couple of hints here is try to generate a model that is monolithic, meaning um, if you generate one mesh for this entire big thing, um, it might have some interaction going on at this edge. You want to make sure that these two parts are separate, because if you have the same node number here from these two parts, then you're not going to be able to capture what is the force in these rivets or in these bolts. So you would have to think about that a little bit. What is the so again, try to keep the model simple. You don't try to create too many parts, otherwise you have to define how these parts interact with each other. And one example that you can follow in Abacus that is similar to this is, let's see, if you go in the same getting started Abacus manual, this appendix C, um, this creates this type of a model. So here two two or three different parts. You have you have a rod that is going through these things. This one is actually free to rotate, but this will give you some idea of how you can actually create these types of parts and how you would create the interaction between them. Um, so another problem that you could take a look at is this reinforced concrete beam. So um, if you choose a linear elastic material for this concrete beam, and let's say there is no crack in the middle to begin with, and if you choose then to model this concrete beam with a rectangular cross section, and then you can create two separate cylindrical rods for the steel part. So within one model, you would have these two different materials. One material is concrete, and another material is steel. Uh, but if you choose the linear elastic material model for both of them, then what is going to happen? Concrete is not does not have much strength in tension, right? So at this point, ideally, the concrete should have cracked, and uh, the entire load should have been taken by steel. But if you use a linear elastic material model, that is not going to happen. So to model more accurately the behavior of these reinforced concrete simply supported beam, you can introduce a small numerical crack. Okay, what we are doing here is you can create a small uh, part on the left side, similar part on the right hand side, and have a little bit of a gap between them. And then if you create these two rods that are going through the gap, that will be a more accurate depiction of what is actually happening in a reinforced concrete beam in reality when you test it. So you can play with different parameters of this problem, maybe the size and the number of bars, what is the depth or width of this numerical crack, can you replicate what is the moment carrying capacity of this uh, center section. Um, similar things you can do for beam column connection, or this corbel, but any other problem that you want to do is also fine. Maybe if you are in geotechnical, you can try to simulate the behavior of the lateral capacity of a pile, or how does soil and abutment react. Um, so so this is the three stages that you would need to uh, do for this project. So sometime next week, this is April 7th, which is 1 week from today, you have to submit what you want to do. So just a couple of pages where you need to give me the problem title. You can again collaborate with your, if you are already working with a couple of other students in the class, that's fine. You can collaborate on that, but all the project report that you submit has to be your own. Um, and try to model or try to study a particular problem. Finite element analysis of something is not enough. So here I've given you a couple of guidelines also, how to choose, how not to choose a big problem, or and make sure that you don't have, make sure you have enough time to complete this problem. So uh, define different problem parameters, define these different types of meshes. So ideally, you should actually create a geometry, try to mesh it, try to see what you initially get, how hard it, or how hard or how easy it might be to do a certain type of problem. Um, and this is also sort of important for the proposal stage. What are you trying to, what kind of uh, behavior would you expect from this type of a problem? Uh, is your model going to be able to capture that behavior? Uh, so it is not necessary actually to try to create a very accurate or very detailed model. You can capture quite a lot of things by even simplistic models. If you try to make your model too complex, Abacus might just not work. It might not converge. Okay. Um, so I think in the week after the midterm, which is maybe next to next week, you have to also submit a progress report, and that is worth 10 points. And again, all these points are sort of flexible. If you, at the end of the project, um, if your project is in good shape, then I might be willing to shift around the point allocations in this. But in the project progress report, what I would like to see is that you have enough number of results, and you have done some verification of your model. Verification meaning that what the results that you're getting out of your project are they valid? Do they make sense? You can verify those things with small hand calculations or by refining the mesh and seeing whether you're getting the same value or not, whether it matches your intuition or not. Um, so actually you can use advanced capabilities, but again, try to keep it simple. There are quite a lot of things that you can study with simple models also. And finally, in the final report, what you would, the emphasis is going to be on results and the discussion and insight. So what I would say is that by the time you submit your progress report, most of your analysis should already be done. So the final report, which is a couple of weeks after that, so this is due sometimes in the final week, but latest by the last day. Um, in this part, the emphasis should be on interpreting your results. And what insight did you get? What did you learn from this project? Um, and there is no minimum or maximum page limit, but try to be brief and to the point, but still you need to have enough detail in there so that I can make sense of what you've done. Okay, so let's stop there, and I'll be available pretty much this week, next week. If you want to come by my office and talk about what project you want to do, that's fine too. All right, so see you on Friday.